Recording. Okay, good. So we started recording. Welcome to class for today. We're just going to do a little bit of RNN. I don't want to go too long. The topic is it's very interesting, kind of clear. So the slide, I don't think we need to go for too long today. So RNNs. So what is the motivation behind RNNs? Is RNNs inherently they have a temporal, right? There is a temporal aspect to RNNs. So so far we are seeing classification problems and we're seeing a regression problem. And you can imagine that another fundamental task is the prediction task, okay? So imagine, for example, that you have a certain sequence of frames that comes from a camera and you want to predict what's going to be in the next frame, okay? So the idea here is that if you're given this horrible frame of a person halfway through a door, right? Two options are possible, that either the person is leaving or the person is arriving. Okay, so the idea is that if we ask a network to do this, the correct way to frame the problem is to add the temporal aspects to our data. So now our data would be associated with a temporal sequence, and we put the temporal sequence in the network, and the network predicts the frame number 4. Okay, so it takes frame 1, 2, 3 to predict frame number 4. Once frame number 4 has been predicted, then frame number 4 would be revealed by reality, right? And then we're going to use frame 2, 3, and 4 to predict frame number 5. Then after frame number 5, we're going to see what is the occurrence of 5, and so on and so forth. Okay, so this is a prediction task in a time series, and the idea is that you're doing next token prediction, next image prediction, next label prediction, and you have a temporal sequence, so your model will slide along the temporal sequence and do the prediction. And after the prediction is done, then the reality will occur, and then we slide further down. Okay, and we keep doing this. And these models are usually referred to as a sequential model. Sequential meaning that there is a certain temporal sequence. Okay. The sequence needs not be temporal, right? Could be spatial, could be whatever. But the idea is that the data comes to us in a certain stream, and the model takes a chunk of the stream, performs a prediction task, and then we continue forward. Okay, so you see that here there is this duality, right? In the sense that we don't have labels anymore; we just have a sequence. But the sequence is revealed to us as the model progresses during inference, right? The model is revealed to the data is revealed to us in a streaming fashion, right? So that now we do not imagine that inference occur on a single element of reality, right? But we assume that our inference is taking place over a sequence of data, over a stream of data, and at each instant we are predicting something about this stream of data, and after the prediction, reality will catch up with us, and we have to sequentially produce predictions. Okay. So the idea here is that what we want to do is that we want to do windowing. Okay. So the idea is that since we obtain the observe this streaming data, we want to take a window of the streaming data and use this window to do the next sequence prediction. The predicting the next entry in the sequence. Of course, you understand very well that the window has a certain size, and the longer is the size of the window, the better prediction we have, but we have a scaling up in complexity, okay? Because the input of our network, they are growing in cardinality, okay? So this is what happens. The idea, though, is that if we take a window, right, we have the issue that the memory, right, of the window is contiguous cells. Okay, so we observe contiguous entries in our stream, and the idea is that, for example, if we look at this specific window, right, we see that the doggy is entering from the door is closing, then the door is opening again, and we would like to know what's in the next frame. But if we just base our prediction on the finite window that we have before us, then we have no clue of what's happening next. Okay, meaning that we don't know if if somebody was taking the dog out, and if the person that was taking the dog out was a male or a female, if they had a hat or a cap, if they were wearing a jacket or a shirt. So if we were able to have a longer window, we would be able to determine this, but we do not want to pay the price of keeping a memory which is so large that remembers so many different entries in the stream. So what is the idea is that we would like our window, right, to be able to pick relevant frames in the previous sequence, which are not necessarily contiguous. Okay, so what we would like to do is that we would like to have a context, okay, and keep and forward the context with our current window, so that our context can remember relevant information. So, for example, here we see that there is the stickman that leaves, then there is the dog that follows the stickman. So that then in the next context window, we know that after the dog, the stickman is going to come back. Okay. So in this case, for example, there is another example with the stickman. So the guy wakes up, he wears a hat, he wears gloves, he listens to music, and he goes out. Okay. So when this guy is going to come back from work, hopefully, he's going to repeat like even if the guy goes out of frame, then we should have a mechanism in our network that remembers that the stickman did this sequence of action. So when he's going to come back into frame, he's going to have gloves and music and hat and so on and so forth. Okay, so in order to do this, we have some sort of an idea of context which is carried out. Okay, so the idea is that we take a frame and we produce a certain embedding, right? We produce some context for the first frame, context for the second frame, and so on and so forth. And then the question is that how we're going to carry the context out. We need the network to tell us this. Okay, so let's continue with this example here. So W4 will indicate that the person is listening to music, so we can teach the network to give us a certain embedding if the person is listening to music, and this information maybe doesn't have a lot of importance because by the time the guy comes back into frame, he could have decided to stop listening to music. But wearing a hat, right, would be maybe more relevant for the next prediction, because if the guy left the house with a hat, it is very likely that he didn't lose the hat on the train and he came back with the hat again. Right? Same thing for the gloves. There is the fact that the guy is wearing the gloves should remain relevant, because again, unless the guy forgot about it or there was a change of temperature, when he's going to come back into frame, then again he's going to wear the gloves. Okay. So this means that we have to be able to associate the different weights to the different to the context which is extracted from each frame, and this is something that we would like to take into account when we design our next network architecture. Okay, so what is the desirable properties of the networks that we are envisioning? So it has to be able to handle variable length sequences. So in our mind, data comes in a stream. The stream has a certain length, so it has to be able to be sequential in this sense. It has to be able to keep track of long-term dependencies. So if something happens very much in the past, and we should have some sort of memory mechanism, right, that stores the relevant information in the past and maintains it for the next prediction. And there is an idea of order, right? There is an idea of order in which sequences are in which information is received, and we should be able to share parameter across the network. And so when we think about this, we encounter RNNs. Okay, so an RNN is obtained as follows. So imagine that there is a feed-forward neural network, which is your usual network, and it takes an input vector X and it produces an output vector Y. Now, this one here doesn't have an idea of memory or an idea of context. So what we do is that actually we imagine that we are stacking this network temporally, right? We unfold the network temporally, and we apply the same network to each of the entries of the of our input stream, and we allow for this output of the network, which is also the input of the network at the next time instant. So at time 1, the network is going to take the input x1, and it's going to produce 2 output. One is going to be the output y1, and the other one is going to be the output h1. And the next instant, this h1 will enter in the network together with our next input in the stream, which is x2. And together, they're going to produce 2 outputs. One is y2, and the other one is h2. And this continues throughout time. And this is how we handle sequences, okay? So when the network is unfolded through time, you imagine it to be as this sequential, this unfolded operation, right? So that the word here to use is unfolded, meaning that it's as if at each point in time you use the network. And so what you do is that you unfold the time on the x-axis. So they get this idea. Sorry, guys. There is this idea of unfolding over time. Every time my wife that I'm teaching class, she doesn't pay attention to my schedule as other people would. Teaching, class, love. Sorry, guys. And so so when we refer to this unfolding, we refer to the unfolding over time. And alternatively, right, we can represent it as a recurrent neural network, okay? So here it's recurrent in the sense that we imagine that time is flowing, right? So we represent it as a filter, right? As a filter as we see it in signaling system. So the output of the network recurs onto itself, right? It's like recurrent as we discussed, for example, recursive filters, recurrent filters, this type of recurrent relations, right? Z transform, that type of expression, okay? So on the left-hand side, you have the unfolded representation of the network, and on the right-hand side, you have the recurrent representation of the network. And nothing strange here. So everything should be clear so far in terms of how we do inference of the network. The idea now is how do we train this object, okay? Because of course we have this recurrent relationship here, right? So we have the age of t is equal to fu of v, age of t minus 1 x of t, and the inference will be y of t is equal to this fu of v, gu of v of x and age of t minus 1. Okay. So how do we train this object? That's where we have to discuss and think further. Okay. So let's look at this recursive relationship. So the state age of t is the one that we are producing. The fu of v is our usual parameterization of a deep neural network using the parameter uv. Age of t minus 1 is the old state, and x of t is the current input. Okay, so this recurrence relationship is saying that the next state of the neural network of the RNN is obtained as a function that we have to learn, like a learnable function of the past state and the input. Okay. Okay, so now we start thinking, and it's clear that we're getting a little bit confused because we still have to train this object, right? We have to learn this object, and we're asking ourselves, how are we going to run backpropagation on this? Okay. So before we go there, let's just think a little bit about nomenclature, calling things, giving name to things. So age of t is called a hidden state sometimes, or a state, or an encoding or an embedding, okay? Multiple names to describe multiple roles that this can play. So if we describe it as a state or as a hidden state, we are thinking that the reality follows some sort of hidden Markov model type of representation, or and then we think that there is a state of the world that is being learned by the network. Then there is encoding or embedding. This is more of a autoencoder type of architecture, right? So we think that we are extracting some information from the world and we are putting it into an embedding. Okay, so you guys have seen embeddings in the challenge number 2. So this is the way in which I use the word embedding. And yeah, and then there is this function, which is what a neural network does. And so we can continue here. So let's see now what is the representation of this network using some flowchart type of representation. So here we have a set of hidden states. Of course, we have a certain number of units, right? So how many units we decide our state that needs to be. Here we have the input, right? So the input, again, will have the state which is controlled by, will have a size which is controlled by the process that we're doing. Here we have a deep neural network, right? So whatever happens here can be learned. And then we're going to have a set of dense layers, and then we're going to have an output, right? So let's say a prediction of what happened in the next task. And for simplicity, let's just say that this is a tonnage of whatever happens there. And of course, the output, we could be doing classification, we could be doing segmentation, we could be doing next token prediction, we could be doing image generation. So many possible architecture that we can consider here. Some details about the bias, right? So the question that comes now is, how do we train this object? Okay, because we understand how this object works as a let's say as a learned filter, right? With a certain hidden state, but still we don't know how to train it, and that's the biggest question. Okay, so remember that the easy thing is the forward pass. In the forward pass, we take our stream, we put the stream in, and as we put the stream in, the context is generated and is passed along the line, and then we have a certain set of outputs. Very good, that's the easy part. Then what do we do is that we can compute the loss between the true output and the predicted output, of course. So we imagine that we have observed the process 2 times, so we know what the true output would have been. So that both the input and the output are some learned sequences. And after we compute the loss, what do? We sum the loss across all of the different points in the stream. And then what do? We compute the derivative of this total loss with respect to the parameters. And then the beauty comes in, right? We backpropagate, right, the loss in each of the possible entries of the stream, and we calculate, we do backpropagation, right, of the loss at time 1 with respect to the parameter, or with respect to the output at 1, loss at 2, output at 2, loss at 3, output at 3, and then this loss propagates to the network. And now we are a little bit in trouble. We have to make sure that everything makes sense, right? So what we want to do, of course, is to take the partial derivative, right? Oh, sorry. The partial derivative, right, of this core network. And we are a little bit in trouble here because, first of all, this network is the same network across all of them, right? So while we can compute the derivative at each point in time, we are in this pickle that we don't want to have n different neural networks. We want to have just a single neural network. So we have to decide what we're going to do with all the gradients that we calculated at different point in time. And of course, the answer is that we're just going to average it. Okay, the beauty of stochastic gradient descent is that averaging of gradients always works as a rule of thumb. So here we're going to say, well, each network should have behaved differently, right? And we have a gradient that will bring each of these networks into performing better at that time instant. And we're going to disregard the time dependency and just average everything out and just obtain one single network, which is updated as the average of the changes, right? The average of the model updates at each point in time. And then there is this other issue that we have, which is the dependency of the age 1, right? Because the context, right? The context here, in a sense, where do we take it, right? Because the context comes from the next time iteration. So how are we gonna do this? Well, we're going to do the following. There's going to be a last state of the RNN, a last state of the stream, and in that case, the context, right? There is no context that the network produces. So what we can do is that we can derive we have the derivative of the loss function at time n with respect to the context at previous time, so h of n minus 1. So for sure, what we calculate is the derivative of the loss with respect to the last state that was inputted in the network. And then this object is backpropagated from time n to time n minus 1. And so we propagate back this gradient all the way to the first state of the string. Okay? So remember this, right? So there is sort of a causal dependence here, right? Because at time 1, we would like to have the derivative of the network, right? That produces the state, okay? But we in a sense we haven't calculated that yet, because this is calculated the next time instant. So what we do is that we backpropagate in a sense through time, and we look at the last state, and what we can do is calculate the derivative with respect to the context that was received at the last state, and then we backpropagate this back all the way through. Okay, so remember, this is how the backpropagation flow, how the computation of the computation network, the backpropagation is. So here we propagate the global loss into all of them. Then we go to the last state and we propagate the derivative with respect to the context, to the hidden state. And then all these model updates are then averaged out to the final RNN. Okay, very beautiful. Yeah, so everything works out. During backpropagation for each parameter at each step I, the gradient I is computed. The individual gradients computed are then averaged at time step t and used to update the entire network. The error flows back in time. Okay, so you see that the loss with respect to the context, so u is the context here. You see, guys, u is the context. Derivative of the loss with respect to the context is the derivative across the context through time, right? From time 1 to t. And you start with the derivative. So this derivative accumulates in time, right? You see that you start from t to t minus 1, t minus 1, t minus 2, all the way back to t equal to k. Okay? And then the derivative of the loss with respect to the context is the average, right, of the derivative of the context with respect to the last time instant, the time instance t minus 1, t minus 2, all the way back to t equal to 1. Okay, so very beautifully this works out just fine, and quite incredibly, RNN work very well. And you can try yourself and see yourself that this actually works. But of course, computationally, it is very problematic to backpropagate over through this long chain. Okay, so let's say that you have a time series of electricity prediction for the past 10 years, and you have maybe hourly electricity predictions. Are we really expected to be able to backpropagate across, let's say, a few million different time instances? Of course, the answer is no. So what you have to do sometimes is that you have to monitor your gradient, and you fix this backpropagation to a certain window. So you assume that you do the prediction for a certain n states, and at the end of it, you check the stability of your gradient. And we said it multiple times, the gradient does two things: either explodes or vanishes. And you sort of try to calibrate your hyperparameter, your learning rate, your window size, so that you have some numerical stability when you choose a certain backpropagation window, and you avoid the numerical instability that comes with a particularly long training window. Of course, the trade-off is clear, right? So the larger the window, the more you can learn about the long dependency of the context, right? So imagine the example before. Let's say that the person leaves at 8 in the morning with the hat, and you want to remember until the guy comes back at 6 p.m. with the same hat, right? So if this is a surveillance video, means that we have maybe 8 hours of videos to go through, and you have to remember for these 8 hours about this context, right? So if you don't train the network over these 8 hours windows, then the network is never going to realize the correlation between putting on the hat in the morning and coming back with the hat at night. So clearly you want the window to be as long as possible, because you want to capture dependency that has a very long time correlation. But of course, the longer the window, the more unstable the training is. Either the gradient vanishes or it explodes, so that the numerical trade-offs are clear, right? So as an algorithm designer, you have to design things so that so that your network performs the job that you are trying it to do, right? So there are not too many definite suggestions, right? I can just point out what are the trade-offs in the training. Okay, very good. So this is sort of the first time that we see this type of sequential networks. We're going to see multiple instances of this sequential network. As you can imagine, this is a new class of problems and applies to many different contexts. So we're going to come back later to this. And the first thing that we do is that we see bidirectional RNNs, okay? So very easy to understand what is the variation that we have here with bidirectional. So right now we imagine that the flow, right, is sort of a temporal flow, right? So the data comes in a stream and the stream proceeds in time, but often, right, you have access to the full stream at one point in time. For example, if you have a video recording or if you have sort of spatial property, right? Then what the network can do is they can move back and forward in time. And so the context window that you consider can be both both below our time instant t and above after our time instant t. And so in this case, it's clear that you sort of want to do the prediction of your context t coming from the left and coming from the right, okay? Coming from the present and coming from the future. Very good. So this is clearly an easy variation of what we have, which applies to instances in which the stream is during inference time, the stream is present. The stream presents itself with a certain temporality that allows us to come from the future and come back to the present. And the architecture that we want. So for example, text, right? Text is such a case, right? So you have a stream and you can predict, you can use both the present and the past words to predict the current word. And so what you want to do is that you want to have two models, right? You have a forward model that goes from the k less than t and predicts the current context, age of t. And you have a reverse network that starts from the end of the sequence and comes back. Okay, so these two networks are trained independently and they run independently. And as in a single point in time, what you do is that you take the forward context and the backward context, you stack them together, and then you do the prediction based on this. Very natural, very easy to imagine. Okay, so the networks are now three components, right? So this is the prediction head that takes the forward output of the context and the backward output of the context network. So this is the forward RNN. So it takes the indexes from 1 to t, and it does the prediction of the next context. And this is the backward network that runs from the n and goes to n-1, n-2, and so on and so forth, and then stacks it inside the context that this prediction network sees. And the question is, how do we do the training? This should not surprise you, right? So this is like two networks that are stacked in parallel, and you're already seeing that in your computation network, it's very easy to move gradients across networks, right? So you will compute a loss here with respect to the output, and this loss will be propagated from the recurring to the current state, from the future to the future state, and then you build again the computation network of a certain window, and then you average the weights of the weight updates of this network and the weight updates from that network over the window that you've chosen to train on. Okay, so of course you have the same issues as before, meaning that you have a certain length over which you do the prediction, and there is some numerical instabilities, right? So you hope that your gradient doesn't vanish, so then actually you can update these networks, and there is a certain stability, and you understand that now that we have not one network but three networks, there are more hyperparameters that we can tune, more things that can go wrong. So it's the trade-off is again clear, right? So we're increasing the complexity of the simple RNN to get to some better performance. And now we go to the deep RNN. So here we saw that in bidirectional RNN, we figured out that we could come from the future and the past. What happens in deep RNN? Well, what happens is that we can have multiple layers, okay? So it's clear that what we can do is have an RNN that predicts a state and then build an RNN on top of this state, okay? So you might look at this. So we have the first input. The RNN produces a certain age, and then another RNN takes this age as an input and produces the Y. This is the equivalent of, of the multi-layer perceptron, right? It's as if we have some intermediate representation, right? And this intermediate representation is passed down to the next RNN. Of course, you can have that each RNN is a deep neural network. That's okay. That makes sense. But in a sense, the temporality of the network is still reduced to your window. What you can hope to do, right, is that you can increase the temporality by stacking RNN, let's say in this temporal depth, so that the time instant, a certain context, a certain layer, has a certain window of time over which the context is collected, and as you repeat, as you move through the layers, right, the layers are able to get a larger breadth of temporal information. This is a little bit similar of what we are doing with convolutional networks, right? So we said, oh, well, a single convolutional layer is nice because the output of the network takes a certain patch of our input sequence, and we said, well, if we stack multiple convolutional networks, then in a sense, what we are condensing at the deeper layer of the convolutional stack is a larger spatial characteristic of our image, for example, so that we gain expressivity by being able to capture global features. And this is similar, right, in the sense that if you want to increase the temporal spread over which information is collected, then you can stack multiple RNN on top of each other. Very good. Again, training is the issue, right? Because as we have more layers, then the backpropagation gets more complicated. We have windows for the certain RNN. We have the window for the next RNN. Gradient have to be passed, and so on and so forth. But we understand something we gain something fundamental here, which is the idea of these ages, okay, of these intermediate age values, intermediate context and embedding. Because in a sense, right, our networks produce an input, and we have not designed this network produces an output, and we have not designed this output to be anything that it's understandable for us, right? We don't have any loss over this object, so this object can be anything. So it's clear that this is some information in the network that is extracted from the sequence, but it's not interpretable for us, but we have this understanding that it's maybe something useful, right? So let's say if you want to then create some description of the image, which is learned on the task that we are trying to perform, then this is what you will do, right? You will just look at these ages and be like, I don't know what these ages are. They are not interpretable for me as a human, but the neural network thought that they were useful. So that's something that we can keep and try to use for some other downstream task. Flavor of RNN. Okay, so the RNN by itself, it's kind of useless, right? Because it takes a single input to produce a single output, not very useful. What we can do is that we can have a one-to-many mapping, okay? So you can have a single input, right? Goes into the RNN, and the next RNN, they just produce an output based on the context that you were given to it. And this is a one-to-many RNNs, okay? So imagine that this is a network that creates a song. So this is your initial prompt, right? Make a song in the style of Mozart, and the RNN starts producing a temporal sequencing output, right? So this is what your Suno does, right? There is an embedding of what you're doing here, and then the network is sort of feeding onto itself, and it's producing multiple output. So this takes a scalar, and it produces a temporal sequence. Whoop. Then you can have the many-to-one case. So, for example, let's say that we're doing sentiment analysis on the song. So these are the notes of the song. They go into the RNN, and the RNN keep accumulating the flavor of the songs, the meaning of the song, the context of the song, and this is passed down, and we ignore the output of the network until the very last node, and then we apply the loss function only to the last node, and then we hope that the network learns to summarize the sentiment of the song through this specific architecture. Okay. The many-to-many is the one that we saw before. Let's say that we are predicting the weather, right? So this is the current humidity, and this is the current temperature, and we try to do the prediction of the time sequence as well. And this could also be language modeling, very importantly, right? So it could be that this is a sentence in English, and this is a sentence in French, and we are teaching the network to map from one language to the next. And this is an example of language modeling, meaning that here we're doing next token prediction. So here, let's just say that we use words for our simplicity, but we know that what we want to do is tokens. So the sentence that we have, it's a good time to be alive. Well, there's no time. It's good. Oh, okay, it's good to be alive. Okay, it's good to be alive. And we want to teach the network to produce language from a certain input. So what we do is that we produce its, we ask the network to produce the next word, which is good, then we give it good, that's to produce two, and so on and so forth. We train the network to do this. And then it's clear now that once the network is trained, it will be doing language prediction, right? So you will put in a word, and then the network will produce the certain output, okay, during inference time. Okay, so another example is language modeling with a many-to-many network where this happens, right? So this is the first language. And at the end of the first language, or after a certain delay in which the first language is produced, then the network starts producing the other language, right? And this is because when we move between languages, there is a different organization of the sentence in terms of order of noun, adjectives, and verb. So you cannot do the translation in a sense synchronously, right? You cannot map its to L and open to abrir. So we have to allow the network to have a certain desynchronization between the inputs and the output. And so this could be your first sentence in English, and after 3, 4, 5, 10 words, then the sentence in Spanish comes in, and then you teach the network to do translation by considering the loss over the structured sentences, right? The final sentences in English and the final sentence in French. Okay, very good. So time for a break. Let's take a 10-minute, let's take a 4 minutes break. I'll see you back at 15. We do a little bit more presentation, and then I'll let you guys go because too much talking from my side, okay? Okay, I'll see you back in 4 minutes. Walk around, get some water. I'm gonna get some more coffee, okay? Ciao, guys. Hello, guys. We're back. Let's see if there is any more questions. Otherwise, we do a little bit more. We can do some BLSTM stuff. Should be okay. Any question from the class? Any questions from the class? Otherwise, we go with GRUs. Let's see that Nafal joined us. If you have any questions, you can also ask Nafal and Simon, our greatest TAs. Okay, good. So let's do some GRUs. Get to the recurrent units. So we discuss RNN, right? So we said that they can handle a variable length input. They can keep track of long-term dependencies. They remember what order is, and you can share the parameter across the network. Then we said the shortcomings is that you need to train over the previous hidden state, and backpropagating through this, it's kind of hard because you need a long window to capture enough dependencies to be interesting, but you pay the price in terms of complexity and stability of the training. And yeah, and the way in which the context build, it is not clear to us, right? So imagine that we have this prediction of a sentence, right? So we have a sentence in English and we have to translate it in Spanish. And as we said, English put the verbs, put the noun, the verb, the adjective, whatever. But in order for us to do a good translation in Spanish, we have to remember that Spanish has adjectives, right? So, for example, butter, right, will need an adjective in front, right? So if we do the translation one-to-one, this will not work. So we need to sort of have a certain lag on the input before we start producing the output. And so in a sense, the context has to keep squeezing information, right? Has to keep compressing information because we don't want to lose anything important, right? And so the way in which the state builds meaning and context, it's kind of complicated because there could be a lot that we need to store there, okay? So ideally, what we would like to do, right, is to have some sort of idea of a variable way in which we can store the context, right? We will want to have an idea of, at a certain point in time, being able to pick which context is more relevant for the current output instead of trying to stack everything together, okay? So we want to train, we want trainable weights for our network. Let's just call them VNU, that somehow incorporate the input and the previous output. And we need to solve the vanishing gradient problem so that our network also learns from inputs at the beginning of the sequence. Okay, so this is the problem that we're trying to learn. Okay, so we want our weights to depend on the context, but we want to be able to capture long-term dependencies. Okay, and this introduces us to recurrent GRUs, gated recurrent network. So what we want to do is as follows, right? So let's look at this example. So this is our age of t, right? And so we will want to put something here at the beginning that instantiate the set of weight v as a function of our network, so that we observe a certain v equal to x of t first, and then here, right, this u is instantiated by the same age of t and x of t, so that the network learns to adapt the weights to whatever adapt the weights according to the current input and the current state. Okay, so we want to sort of have the ability, right, to select an instantiation of our network, which depends on the input that we have. Okay, so let's go a little bit forward. This is just a second. Just going too long. Set of slides. It's not going to the. It's not going to the. Let's go here, and then we get back. Okay. So this is the image that we can start, and then we can elaborate from here. Okay. So now this is the type of cell that we will want to have. Okay, so think of this as a programmable cell, as a programmable memory cell, but you are able to learn what to store in memory according to the current input and state. Okay, so the input x of t comes here. Okay, and it controls this sigmoid, and the state comes here, and it also controls the sigmoid. Okay, so that what is stored in the current state is a certain activation, which depends on a control signal, right? We will refer to this as a control signal, and this control signal is a function of the current input and state, and this is this age of tilde, right? And then what we put in the next context, right, is this is the current, the past input, right? The past input, or an updated of the state. Okay, so let's see what is this product. This is a Hadamard product, and the Hadamard product is here. Sorry, they're going back and forth, guys, but this is the Hadamard product. So basically, we want to have sort of multiple memory cell and decide what goes into the memory cell using this sort of control signal. Okay, but this control signal, of course, it's easier for us to imagine it in a matrix version or in a vector version. So this is where the Hadamard product comes in. Okay, so you see that here you have a certain matrix, and here you have another matrix, and the Hadamard product is simply the element-wise multiplication of this, right? So the first two entries are zeros, and these first two entries are 1 and 2. The Hadamard product is simply the product of these elements. So the first two elements are 4. Here we have 4 times 1, 4. 5 minus 1 minus 5. So you got the idea of what this Hadamard product does, right? So it's element-wise multiplication in the matrix. And if you do it vector-wise, then vector-wise is the same. It's the same operation, right? And so you see here that what our network is doing with this product, right? It's imagining that this memory is a certain vector, right? And we have a control signal z of t, which is the one that we have obtained from our input and our state, and this decides how the memory vector is updated. We can either keep the old context, right, or we can update the context with the h tilde information which we have obtained. Okay, so let's decompose this. So the age of tilde, we understand, goes into the memory according to the control signal that we have, and now do we generate this control signal z, right? So the z here is a certain network that takes into account the current input and the current state plus some sort of bias, right? And what goes in the memory is controlled by this R, right? And this R, again, is controlled by the current input and the current state. Okay, so here the representation. So the age of t minus 1 comes in, and the age of t goes out. And what we put in this state is as follows. First, we prepare an age tilde. And then we decide what to store inside there, right? According to this weighting using the Hadamard product. Okay, so it's a little bit, notation-wise, it's a little bit messy, right? Maybe we have this for equation, but the meaning is clear, right? So we want the network to decide by itself, right? To learn how to update its own state, so that if there is some part of the context that should be remembered for the future, then we have a control mechanism it's a learn control mechanism that decides what should be kept and what should be updated. Okay. So a little bit of names here. So the R is the R for reset, right? So the R is the capability of resetting the memory, right? So you see here that there is an accumulation of the t minus 1 Hadamard timely reset, right? So if this reset says, well, we are all zeros, then the memory gets completely vanished. And Z is the update gate, and you see that Z is the control signal, and you either accumulate, and imagine the Z to be 0 or 1, right? So because this is a sigmoid, so it's a signal that is either it's between 0 and 1, and you can imagine that it has been trained to produce something very close to 0, very close to 1. So if this were binary, it would decide what to keep and what to throw, because it's Z and 1 minus Z. So zeros are flipped to 1 and 1 are flipped to zeros. So what goes in the next memory cell It's either what was in the past or how things were updated in the present. And the update, right, either depends on the past, or if there is that gate is on, only depends on the current inputs. Okay, so this is current input. There is that gate tells you how much you should care about the past, and then this gives you the H tilde, and then the update control signal, right, decides what to keep from the old context and how to update the new memory cells with new context. Okay. So what we hope to do is that we hope to be able to, to solve some issue with trainability of RNN. So if you try to train an RNN, you will realize that RNN are kind of stubborn to train, because, as we said, it's very hard for the network to learn well what to store from the past. And so people introduce GRUs. The second, all right. So what GRUs were introduced to sort of obviate this, right, and allow a more efficient training, but they have the disadvantage that we have to learn this control signal. Okay, so you understand that for this Z to learn to work effectively, right, the sigmoid should be very steep, right? We should be operating in a regime in which the Z is almost a binary signal, right? It's either 0 or 1, so that we really have a meaning of a control signal. But you understand that the sigmoid is controlled by a temperature variable, right? And it is hard to train when the temperature variable is very high, and so the transition is very fast. So what you want to do, right, is at the beginning of training, you want to have a certain smooth version of the sigmoid, so that the control signal is not too sharp, and so that when you do backpropagation, your gradients are not vanishing or exploding. And then as the training goes on, you try to sharpen the sigmoid to be more and more similar to a control signal. And so this adds, dynamics to the training, which means that it's more hyperparameter tuning, more experience, more iterations, more data. So we have only partially obviated to the issue of having to train a network that operate on streaming data. Okay, let's do another little bit, I think, and then I'll let you go. GRUs. Let's do a little bit of LSTMs. Let me know if you have any questions about GRUs. Of course, you have to have your own experience with these models, and this is our goal with the next challenge. Okay. So we discuss we discuss RNNs. We discuss GRUs. Okay. So this image here of the GRU with the green field, you see it in 50% of the paper on sequence modeling. So this is a very famous picture, and I bet that somebody did it in maybe in PowerPoint or in Google Slides or something, and didn't know that the figure will become so famous, right? So when I see this very pale green, it's a little bit. It's not very inspiring for me, right? It's not very futuristic to me to have this pale green, but I understand that. And the people that wrote the paper, they didn't think that the image would become so famous, probably. Okay, so the strength of the GRUs is that we can decide the influence of the past over the previous one of the strengths of GRUs is that the network learns how to value the past with respect to the present context, right? So we have this idea of a control signal that tells you what to remember from the past and what to forget. But the issue that we have is that the update gates needs to be trained very carefully in order to avoid vanishing gradients, and you need to have more gates if you want to have a better performance on more complex input sequences. Okay. So in order to solve this, we can have a GRU++, right? So we can try to further improve on this. And here is the following, right? So instead of resetting the previous gate, we can reset the candidate directly. Okay, so what are we trying to do here? So let's just call this not to be the reset. So this is the reset signal. We don't call it a reset signal. We call it the input gate. And then what do? So we can now directly use this to find the current hidden state. Okay, so this is the current hidden state. This reset is now the input, and this was the Z before, right? So this F was the Z before, and we just let it be another output. Okay, so here, so we are discussing this, right? So this is the next state. This is the Z. This is the 1 minus Z. But we want this to be an input, and we want to change notation from this Z to this V. Okay. So now this is our update gate, and this H tilde is then the input on that one, right? So the H of T is going to be the F of T other marked H of T minus 1 plus this input H of T delta. But the issue is that this H of tilde can become unbounded over time, right? Because you no longer constrained to be a sigmoid. So the issue is that what happens in that case. So it's a problem that we have to solve. So let's say that we call this C now the memory, okay? So and not part of the state. So then the state will be a tanh of C, and this will solve the problem that this C can become unbounded. So now instead of having this control signal to be sigmoided out, then you keep the C to be your hidden context, and then the memory is produced with a tanh of C. Okay, good. Now we have two different memories, the H of T, which is unbounded, and the C of T, which is bounded, and they are linked together by this tanh operation. Okay, good, but this C of T, it's a little bit unused at the moment. Sorry, this H of T is a little bit unused at the moment because it's simply the tanh of C. So what we can do, we can just add another control signal on this, and this adds expressivity of the network. Okay, so this is the way in which we get to LSTM. LSTM stands long and short time memory, and the idea is this: you're able to keep memory of things that happened in the past, and also happens that things that happen in the near future. Okay, so let's see the whole architecture here. Equations are becoming more and more numerous, so let's try to be patient. So we have the C tilde, right, which is the tanh of the input plus the past state and some bias. Then they have the C of T, which is controlled by this F of T and I of T. And so the CT is the update over the CT of -1, and the F of T is what you keep from the CT. So now here we have a mixing. We don't have this idea of a control signal, which is Z and 1 minus Z. And the H of T is a further modulation of the memory, right? So the H of T will be modulated by this control O, and then the O will produce the H of T, and then the H of T will become the input from the next network. So now here we have this. Okay, so the F produces the output Y, so the F is there. We have the I that controls the memory, and you have the O that shapes the tanh of the C of T. Okay, so these are hidden states in a sense. These are memories of the network, and these are neural networks that we have to learn. And these ones here are learned over a certain window of time. And these are values that we do not control directly, but they are learned by the network. Okay, so now complexity goes up because we have three gates, right? One gate for the output, one gate for the long term, and one gate for the short memory. And this is a vanilla LSTM. Okay. Okay, so now here we have the old LSTM, the old GRU, right? And now this becomes an LSTM. Okay. So the tonnage is here, the tonnage is there. Sigma, sigma, sigma. So these are the three sigmas, right? Sigma, sigma, sigma. One goes to the output, right? So this is the output. And one goes to the short-term memory, and then one goes to the long-term memory. Okay. So just some more ways of expressing this. And we give it the name. So this is your C of t. And the C of t goes forward. Then we have the age of t, and here we have the age of t. Here we have the age of t minus 1, and here we have the x of t. So it just follows the rows, right? So the first F is the one that determines the output. There's a question? Yeah. You guys are not. Yeah, you guys can see the slide, right? Hey, you guys can see the slides, right? Guys, can you confirm that you can see the slides? Why? Mystery. Let me try to start off. What happened to the slides?
Yes, sir. It's not visible.
Oy.
Just a blank.
Really?
Oh,
Sure.
really? But I can.
I think maybe your connection. Well, we start again. You tell me. How is it, Simon? Can you see it?
I might need to reload the web page.
See, when you're in the library surrounded by other students, you don't have that good connection. How about now? Good.
Yes, sir. I see it.
Okay, good.
Thank you.
Okay,
Sorry.
so we're going through this. We're threading through this, right? So we have these sigmoids, right? And we have these memory signals. So the C of t minus 1 is the unbounded memory. The age of t is the bounded memory. The x of t is the input. So first thing that we do is the f of t. So the f of t takes the age of t minus 1 as x of t, right? And it plugs it there. Then there is the I of t, right? The I of t is this object here. And then we have the O of t. And and then you just go through and you see that these are the intermediate steps. But you see that now the network produces the H, the C, and the Y. Here there is no Y of t, but the Y of t is there. Good. Just going through this, fairly simple. So this is called LSTM, which stands for long short-term memory. So the idea is that you want to store memory of things that happened way in the past and things that happened more recently. So introduced in 1995, right? Already too many years ago. We don't want to think how many. And it was supposed to solve the vanishing problem. The training was done using a mixture of RNN learning and preparation through time. It underwent several modifications, adding forget gates and connection and so on. And then, many different variants have been introduced. This type of sequential networks are also good for doing sequence to scalar, scalar to sequence, sequence to sequence, asynchronous sequence to sequence. So sometimes you have no input gate, no forget gate, no output gate, no input activation, whatever. So there is this paper which is called LSTM, a Search Space Odyssey, that shows you all the different versions of LLM that people have seen. A few comments between LSTM and GRUs. So we're going is to compare the performance between the two, right? So how is the difference between the forget gate and the reset gate in GRU and LSTM? And this is something that we'll do in the next challenge. And then the other thing is that we're going to explore is how having these sequences, right, produces a word embedding, which can be used as a downstream task for other different tasks. Okay, very good, guys. Let's cut it for today like this. It's been a struggle for me to have to talk for so much. I feel like, yeah. So next time I'm much more excited because you guys are going to present. Should be much more rewarding for me to listen to you guys than to listen to myself. So we say hi to the people on YouTube. Ciao, guys. We stop the recording.